you very much. Let me start with saying thank you to everyone who gathered here today, and special thanks to Logsoft for organizing this meeting. It's a big pleasure for me to present here for you. So let's begin. A few words about myself. Oh, let me turn on my presentation. Okay, everyone sees it?
Yes, I think we do. Yeah, please, chat in. Could you use the chat to type yes, I can see, or plus, or something like that. Oh yeah, I see a lot of yes.
Great. So, few words about myself. I'm Andrei Pangin. Currently, I work at Одноклассники. It's a large social network with many million users, thousands servers, truly high-loaded and highly scalable applications, mostly written in Java. Before that, I worked at Sun Microsystems on different Java virtual machines, including the most famous one, the hotspot JVM. And in my spare time, I keep answering questions on Stack Overflow. And if you ask a question with and mark it with JVM tag, be sure that I'll see it and will probably answer. And I'm also an author of Async-profiler, our primary topic today. So don't expect this session to be unbiased. But my talk today is not exclusively about Async-profiler. I'll cover general profiling topics. That's exactly where we'll start from. I'll explain reasons behind the Async-profiler, what motivated me to develop it when there are a lot of other profiles already available. There will be enough time for live demo. The second part of today's session will be mostly live demo. Okay, so let's start with this agenda. What the first thing you do when you encounter a performance problem with your application? Now, the profiling obviously shouldn't be the first thing, because you first need to know what to optimize. The bottleneck in your application can be anywhere. It can be CPU, memory, bandwidth, network I/O, whatever. In our production systems, we monitor nearly all resources to find the bottleneck. And once you know where the bottleneck is, so the idea is to optimize the particular place. Okay, but even if you know that the problem is in high CPU usage, it probably not always needed to start with profiling. Like on this picture, you see that there are 4 CPUs, but only one is loaded. So instead of optimizing algorithms, maybe it's possible to use some kind of parallelization and automatically improve the performance 4 times. But when you know that CPU utilization is indeed high, then CPU profiler is your best friend to find what's the problem with CPU usage. Okay, how do we profile CPU in applications? First of all, there are 2 big categories of profilers. The one is instrumenting, They basically trace each method transition, and they usually do it by instrumenting bytecode. And of course, this approach is really slow and not suitable for production use. And it's not useful in production either, because what you profile is not your original application, but instrumented application. For profiling production code, sampling profilers are more appropriate. How do they work? Every small period of time, they take a snapshot of what the application is doing. This is a lightweight approach, and furthermore, you can play with the sampling period, so you can control the amount of overhead. We do use sampling in production in our systems, and my further talk will be about sampling profilers. So how do they do? How do they work? There is a simple, convenient Java API, which basically gives you a representation of stack traces of all threads. So the snapshots of all application threads. It gives you a map with stack traces, and there is another API, native from JVM tool interface. It is similar, except that it has more compact representation for stack traces. Once, when I profiled an application in production, I accidentally forgot to disconnect VisualVM, and as a result, response latency of our service increased by a large amount. So it appears that the profiler do have an overhead, significant overhead, which can be noticed with our monitoring tools. For example, if your application have 1,000 threads, the snapshot of all their stack traces can take as much as 10 megabytes or even more. And the process of getting those stack traces can take a significant amount of time. And obviously, with 50 millisecond latency, you won't be able to sample applications more than 20 or more than 10 times per second. But at the same time, this approach is good because it is simple, it works on all Java platforms, it requires nothing extra from the JVM, and it's supported by many profilers, VisualVM, JProfiler, YorkKit, and so on. In a reply to one of my tweets about profiling, I got this nice response. Well, it's a fair opinion, and I'm not going to argue with that. But okay, let's see in action how, let's say, generic profiler works. So the time for our first demo. This is my favorite example, which almost all sampling profilers fail. This is just an infinite loop, which works while a thread is alive. And what it does, it basically appends 5 symbols to the end of large string builder of 1 million characters, and deletes 5 characters from the beginning of the same buffer. And try to guess what will take the most CPU time in this loop. Okay, let's run and measure with VisualVM profiler. Here is my application. What happens? Yeah. So we need not this one. It's a live demo. Yeah. VisualVM, I press CPU, sampler, profile the application for several seconds. I think it's enough. So VisualVM tells me that 100% time is taken by thread isAlive method. Basically by this simple native method. Do you believe this? Well, I don't. Okay, but many of you probably heard that VisualVM is not perfect for profiling. Let's try JDK Mission Control and Flight Recorder. The same application. I start flight recording, 10 seconds will be enough. So try to guess, will the results be better than those of VisualVM?
Yeah, guys, I think we could use chat to answer Andrei's question. So would be nice to see what you think about. For example, right now you could say yes or no, and I'll speak up the most answers.
Well, what we see is that flight recorder took literally one sample from our application code. Just one sample in 10 seconds, which is in method main and nothing more. So it's even worse. VisualVM showed us something wrong, but Mission Control showed us nothing at all. Okay, what's the problem with these profilers? The problem is in Safepoints. So what are the Safepoints? Hotspot JVM stops all threads in order to take a thread dump, but it cannot stop an application at any arbitrary point. There are certain places in the code where it is safe to stop execution, and at these places, JVM knows how to get a stack trace. These places are usually at the end of the method and inside loops. That's why when you have a long linear piece of code, there is no chance for it to appear in a stack trace because there will be no safe point. There is a great blog post by Nitzar Mokart about this problem of sampling profilers. It's not a new one, but it's still actual. In short, the reasons that the most sampling profilers rely on the standard API to get stack traces, and this API is bad. It's not actually the profiler's fault. It's the wrong API. But Safepoint is not the only problem with get stack traces approach. Another big issue is a native method. JVM has no clue when it is executing a native method, whether what the method is doing, whether it is doing some real work or just sleeping inside a operating system call. Consider this simple example. Application doing a reading from socket in an endless loop. And there are two cases. In the first case, there is incoming data in socket, and the client keeps reading and reading and reading. In another case, the same code works, but there is no incoming data, and the client simply sleeps. If you profile this example in some sampling profiler, we'll see that profiler makes no difference between busy client and idle client. It shows that both of them take the equal amount of time. So in order to get accurate stack traces, we need to avoid Safepoint bias. We need to skip idle threads and to somehow profile native code. And one approach to solve this problem is async GetAllTrace API. This is an internal hotspot API to get stack traces of a current thread, not only at Safepoint. Profiler is supposed to call this function from a signal handler, usually from timer signal handler. Initially, this API was developed specifically for Sun Studio profiler, but such a gem in open source code couldn't remain unrevealed. So other developers started using this API too, though this API is private and not documented and not even supposed to exist at all. A couple of other profilers that use this API are Honest-profiler and Async-profiler. For example, if you run the same example with Honest-profiler, it will show us correctly that busy client takes most time and idle client is really idle. One important benefit of Async GetAllTrace is that it automatically skips idle threads. Basically, because signals from the timer are delivered only to threads that are running on CPU. And Async GetAllTrace can take stack traces not only at safe points, but though it can stack traces not at safe points, to map this stack trace to particular method names, we need to add another JVM option because by default, the hotspot compiler generates debug info only at safe points. This means that if we have several inlined methods into each other, and if you run profiling without this debug non-safe points flag, we will not see these inlined methods. But it is still API to get Java stack traces. It still knows nothing about native code or JVM code. And it doesn't really work on Windows because there are no POSIX signals on Windows. But I put a question mark here because it's actually there is a way to make async GetAllTrace work on Windows, and how this can be done. I invite you to Joker conference that will be in 2 weeks, and Kirill Timofeyev from JetBrains he will explain how he made async get call trace work on Windows. Well, now if we run our very first example with string builder, we'll oh, it's not string builder. Anyway, if you run a string builder example with honest profiler, it will also fail. It will show that large amount of time is spent in some unknown Java error 5. Another problematic example to get stack traces is this simple code. Honest profiler will also show that more than half time is spent in unknown Java error. What is unknown Java error 5? To find what it is, we'll go to the hotspot source code and find this list of constants. So this error means that hotspot wasn't able to unwind the Java stack for some reason. And this is actually a JVM bug. There are certain marginal cases where async get call trace fails to traverse valid Java stacks. I submitted a bug more than 3 years ago already, but there is still no progress on it. However, in order to overcome this problem, in my Async-profiler project, I made several tricks how to manually unwind the top frames to make async get call trace happy. So if you're interested in these particular tricks, we can talk a bit more in details later. Okay, any questions so far about async get call trace, about Java APIs to get stack traces?
Well, I don't see any, but let me take a chance to remind everybody that we have a Q&A button. So if you have any question, please use that section, and chat only for just you know, any information, any other information, non-chat, just comments. And when Andrei asks something, you could answer, and I will speak up your answers and stuff like that. So and of course we'll have Q&A at the end of this hour, and the next hour we'll have an extended Q&A, and I hope we'll have a nice chat about Async-profiler and what you've heard so far, and so on and so forth. Yeah, and there was a question about am I mute by default? Yes, any attendees are mute by default because it's too many of you. It will be unwisable if we let everybody speak up. So in the QA session, I will say you will be able to raise your hand, and we'll let you to speak up. Well, but I don't see any questions about the particular information you just shared with us.
Okay, then let me just continue. And,
No, yeah, if you don't mind, I'll just double check that I understood you correctly. So Async-profiler rely on some Linux signals, right? Or
yes and no. It will be further in my presentation. I'll
okay,
talk
cool.
in details about Async-profiler, how it works.
Awesome.
But before we get to that, let's discuss what else can be done in order to get asynchronous stack traces. Now, not from the JVM side, but from the operating system side. Did you know that every modern CPU has built-in hardware profiler? Starting with Pentium, the processor has so-called performance monitoring unit, which collects various performance counters. Like it can count every cycle instruction, every cache miss, every taken branch, and so on and so forth. Actually, there are hundreds counters in modern CPUs. And PMU may be configured to generate a hardware interrupt once a certain counter overflows. And we can use this scalability to do profiling. So we'll set up a counter, counting some like CPU cycles, and let's say every millionth CPU cycle, I'll generate a hardware interrupt and see what CPU is executing this time. In Linux, the operating system API to PMU is a perf event open system call. So it allows you to subscribe to hardware and operating system events and get notifications when these events happen. So an example of event is the performance counter overflow. It's also perf event open also allows to do some profiling in hardware. So CPU not only generates an interrupt, but it records some state of registers. It can even record a call chain and puts it into a predefined region of memory, a ring buffer, and operating system adds its own information like process ID, thread ID, and then generates a signal to an application. Of course, using this API directly is an unpleasant thing, but fortunately, we have tools that do it for you. The well-known tools Perf. So with these two commands, you can make Perf records events with the given frequency. In this case, we'll take a sample every 1,000 times per second. This is not a typo. Usually it's a good idea to use a not round number, but prime number for frequency to avoid collision with other periodic processes in the system. So once we execute these commands, we'll get a report like this. So Perf tells what processes and which functions are executed and how much CPU time they take. But the problem is we see in this report native functions, we see even kernel functions marked by K, but we do not see our Java methods. That's because Perf doesn't know anything about Java and its JIT compilation. For Perf, these are just some addresses in memory. In order to let Perf know to map these addresses to Java methods, we need to somehow tell Perf this mapping. And there is a GMTI agent that collects this information and creates a mapping file, which is used by Perf. But there is one more trick needed to make Perf work JDK this preserve frame pointer JVM flag. What this flag does? So in order to traverse stack, Perf uses frame pointers. So stack consists of stack frames. So each stack frame represents a function or a method. And these frames form a kind of linked list. So in the base slot of each frame, the base slot of each frame points to a previous frame. And walking through these slots, we can collect stack trace. But how to find the very first, the top frame? So usually the dedicated frame pointer register points to it. But Hotspot JVM by default uses frame pointer as a regular general purpose register. And this preserve frame pointer flag reverses this optimization. So Hotspot no longer uses FP as a general purpose register, but rather make it point to the top frame. This, unfortunately, is not free. So this option may slightly decrease performance. Usually, the overhead is not that much, but in certain marginal cases, it can be as large as 5 or even more %. But the most beautiful part of profiling with Perf is a flame graph visualization. Thanks to Brandon Gregg and his blog, flame graphs became very popular nowadays. With Brandon's script and a few spell casts, we can convert Perf output to cool graphics. I hope most of you already know how to read and interpret flame graphs, but just to make sure, let me do a brief introduction. So how performance profiles are usually visualized? So the most simple and straightforward way is a so-called flat profile, where we group all methods by their self time, the time spent in this particular method, and sort them by the most hot methods. But the obvious disadvantage of the flat profiles is that we do not know where these methods are called from. So tree view allows us to see stack traces, but sometimes these stack traces can be really, really deep, and you'll get tired while expanding this tree one by one. And flame graph combines benefits of both views. So it shows the stack traces in all their depths. So here is a sample flame graph. On y-axis are the stack traces. So the higher is this column, the deeper is the stack trace. So each rectangle is one stack frame. And the length of these rectangles is the total amount of time spent in this method. But it wouldn't be correct to say that it's time, because we use sampling profiler. So we can only statistically know which methods are executed more often and less often. So the longer is a rectangle, the more often this frame was seen in a during sampling. These flame graphs are not just static pictures, they're interactive, can zoom into a particular stack trace and zoom into particular method and see all methods called from this one, or return back. We can use search in browser to highlight all stack frames containing the given pattern. And here we see that stack traces containing pattern class take 30% of total CPU time in this graph. The flame graphs can be colored, so like in this example. So here, a green color represents a Java method, yellow color represents C++ code of the JVM, in this case, the compiler thread. Red one is the native methods, and brown one is Linux kernel code. For example, we want to know what's this red part here. We can zoom and find that Java method nanotime calls a native function clock get time. So the order of these frames on the x-axis doesn't have special meaning. So in this case, they are just sorted by an alphabet in alphabet order. Anything about flame graphs, perf, visualization?
Yeah. There is a question from Sergey Kuznetsov. Could you please shortly describe the flame graph color legend? What does it mean? Which is some colors are red, some colors are green, yellow.
I've just did it. So green is Java, yellow is C++ code of the JVM, red is.
Yeah, he just covered that, Ivan. He covered that completely, yeah. And on chatting, and he's got that covered. There are some other questions, but I think you should keep going. Sergey's good.
Yeah.
Okay, so excited with Perf. I decided to run it, to use it to profile startup of a large web application. And here what I got. What I saw here is a lot of JIT compilation. So this yellow part of the graph, but I didn't see my Java methods at all. It was a Java application for sure. So what was the problem? Instead of Java methods, all I saw is just a big red part with interpreter. The problem is that Perf sees interpreter as a single piece of machine code. It doesn't know what Java method the interpreter runs now. Because the interpreted methods do not follow the general calling convention. So whatever method you execute, the interpreter still the same. So is it clear why Perf cannot show interpreted frames?
I think yes.
Okay.
Yeah, just because interpreter doesn't follow the standard way, right?
Okay, so this is probably the biggest disadvantage of using Perf for Java. It also requires a special agent to decode symbols. It relies on a special JVM option, which is not turned on by default, and using this option may degrade performance a little bit. And it also has some limitations on a Linux kernel level. For example, by default, Perf cannot work more than 127 stack frames. In modern versions of Linux, it's possible to make this limit more. And what I personally don't like about Perf is that profiles generated by Perf are very big. For example, when profiling application for a really large application with 1,000 threads for just 1 minute, it can produce a gigabyte output file. Again, in modern Linux, there is possibility to aggregate this data right away in the kernel without dumping every single sample using the BPF. There are a lot of great talks about BPF by Brenton Gregg, so I will not focus on it right now. But again, this works only in relatively new versions of Linux.